Yes?
Can you do the last problem for the fifth one you said?
The chapter 5?
Yeah, part 2.
Okay. Guess it's somewhere here. Yeah, problem set B.
19.
Well, the last one, right? Oh, that looks long. Oh, yeah, this is a fun one. All right. So, yeah, let me go over it. This is a good illustration of, yeah, it's a good. This is not, well, okay, let me go through it. Yeah. I have a harder examples than this in mind to do eventually. But so I guess the examples I was going to do are more of the collision type. So this is different in that it's a decay. You start out with a single particle that's splitting into two. So I think as a case of a different type of question, it's good for you to see. So let's look at that. So this is, let me just call it particle decay. So for the purpose of the homework question, I'm giving you the exact kind of particle that's decaying, so you know the actual mass. And let's do it for a more general version, and then we can plug in the numbers. So in the particle decay model, this is what you have. You have particle of some mass, and depending on the problem, this particle of some mass could be moving. Let me just double check that it's not moving here. Decays into muon and antineutrino. Okay, so the pion is not moving, so that makes it easier. In the case of this problem, the velocity of the particle is 0. And there are other cases where they won't be 0. We'll probably do that when we do particle physics as part of exam 3. And so after some amount of time, this particle decays. So depending on the situation, it can be more. So it's a minimum of 2 particles, right? Yeah. You can just have a situation where the particle starts out at rest and suddenly it goes off in one direction. Like it's not going to do that. Momentum conservation. So at a minimum, it's going to split into 2 pieces. So one particle of mass 1 going one way, and another particle of mass 2 going the other way. Now, sometimes you might, once again, not for your exam 2, but probably later, exam 3 or final, you might have 3 particles. In those cases, usually the specific situation you are looking for, you could kind of group 2 of those particles together so that it still looks like, at the very basic level, one going one way, one going the other way. This way, you can make the momentum come out 0, and energy and momentum are both conserved. So the conservation of energy and momentum is where you do start from. So you do start from energy conservation and momentum conservation statements. So energy, what's the energy of this system before decay? Hopefully no one here is thinking 0. Rest energy, mc squared. What's the energy of the system after decay?
Gamma m1 c squared plus gamma m2.
Yeah. So this is where you will start to introduce gamma. So yeah, after we write it out, we'll see what the best way to go. But as a default, this is a good way to write it down. Gamma 1 m1 c squared. It's at this point I start subscripting gamma because I have gamma that's associated with one velocity and a different gamma that's associated with a different velocity. So I start using subscripts to kind of keep track of, you know, which is which, so I don't confuse the different gammas. So that's a conservation of energy and conservation of momentum. What is the total momentum before decay? 0, right? So that makes this problem hopefully easier because you know it's 0. There's no complicated expression there. And momentum after, so you have two parts to that 0. It's plus gamma 1 m1v minus the other one going in the other direction, gamma 2 m2v2. So you have two equations, essentially two unknowns. Two unknowns in the form of v1 and v2 because gamma 1 and gamma 2 are expressible in terms of these. Okay? So that's your starting point. And what the question is asking is answer below questions assuming that the pion is at rest before it decays. Muon neutrino has very small mass, which could possibly be 0. Yeah. So yeah, this is where it could involve substantial amount of algebra. And yeah, I remember. So okay, so it's not as easy as I thought it was. So you have two choices essentially, I think. One is to try to solve for these kinematic quantities. And I would say almost never I recommend that you solve for V. If you are going to solve for kinematic quantities, almost every time I recommend that you solve for gamma. Because many times algebra is simpler doing it that way. And the other choice, which is kind of orthogonal to that, it's something to consider if it could be useful, is to use this relationship that at an individual particle level, that this relationship holds. MC squared is equal to E squared minus PC squared. This is the energy momentum relationship. And this is a way to relate momentum to mass and energy without involving any gammas or V. So this would be especially useful if you are somehow given the energy and the momentum of the particles. Now here you're not really, you are not given the, so you know the rest energy of the pion, but you don't really know the energy of the muon or the neutrino. So let me do it in the order it's given. So it's going to feel a little bit duplicative. The temptation I have is I want to do B first, because once you do B, then you can get A as a special case of B, where mass is 0. But let me do A first so that we don't get too tangled up in algebra. We can go through some easy part first and then do the harder part later. So let me do A first. So A allows you to assume a special case. It allows you to assume that if the muon antineutrino is massless, as in, let's say M2 is my neutrino. So in the special case where M2 is equal to 0. In that special case, what else can you say about neutrino energy and momentum?
Momentum is 0.
Not momentum is 0. Momentum is, oh yeah, that's where you actually have to be careful. So this is a good point to go over while we are reviewing special relativity. This formula, P is equal to gamma mv, this is only valid for particles where mass is not equal to 0. If mass is equal to 0, I see where people are saying momentum is equal to 0. Well, I'm telling you, if m is equal to 0, you shouldn't be using this formula, because it's not right. It comes down to, if m is equal to 0, gamma is going to be going to infinity. And infinite times 0, who knows what that's going to be. So you need a different expression that is going to be valid when that formula is not valid. Do you know any other expression that involves momentum that will possibly tell you what that could be?
Lorentz Invariant.
This expression here, right? Energy momentum relationship, or the Lorentz invariant. this is still valid even when m is equal to 0. So this one tells you that when mass of a particle is 0, like a photon, like neutrino as a way of approximation, you have this relationship. The energy of the particle is equal to its momentum times c. So that allows you to rewrite some of these expressions a little bit simpler. For example, here, instead of writing two separate expressions, energy and momentum, I could write these in terms of a single unknown, let's say momentum. So let me do that. So let me do that here. So this is for part A, where with that approximation, things become a little bit simpler. So for part A, we can rewrite this energy momentum conservation relationship as, well, energy, that will be mc squared is equal to the rest of the stuff I have to keep, gamma 1, m1 v, oops, not v, c squared plus energy of 2, which I'm just going to rewrite as p2c. And then the momentum conservation, 0 is equal to gamma 1, m1 v1 minus momentum of 2. All right, so, well, at this point, I have to solve for energy. So this is probably what I would do. I think having this makes it really tempting to actually write these in terms of energy and momentum also. Instead of gamma and v, I would just say, all right, so this is instead momentum of particle 1. And instead of this relationship, I'm going to say, well, energy of particle 1. So the way it's written right now, I have 1, 2, 3 unknowns. So I should really write down one more expression. The m1c squared is equal to e1 squared minus p1c squared. So 1, 2, 3 equations, 3 unknowns, I can solve for them. Okay? So it's going to be asking me for, I guess everything, so I should just go through this systematically. Let's see. What I probably want to do is I think I want to eliminate the neutrino momentum. So let me combine the first two equations together, solve this for P2, plug it in there. Then what I end up with is mc squared is equal to E1 plus P1C, right? Let's see, do I want to square both sides? I don't quite want to square both sides. I think, sorry, it's been a while since I've done this algebra. So when I'm not sure so you've seen this with algebra, right? When you do it the exactly right steps, there's a kind of quick way to do it. But when you don't, then you don't want to be spending too much time just wandering through the maze. This is one trick I have that will minimize that time. Substitution works well most of the time. So here, what I'm going to do is I'm going to substitute in for P1, trying to eliminate it, in the hope that quantities that have E1 squared will cancel out. So yeah, so then what I will end up with is some equation that's linear in E1, and I can solve for that. Once I have E1, then I have P1. Once I have P1, then I have P2. Good. Okay, so let me solve this for P1 first. So that's the plan I have laid out in trying to minimize the amount of algebra I have to do. And this is something that thinking process that you should be going through each time you do especially special relativity questions. because it's really easy to get caught up in the algebra. So P1, let me solve it for P1C, since that's what I'm substituting in. P1C is equal to big MC squared minus E1. When I plug it in here, this is what I end up with. Let me do it in different color. So M1C squared is equal to E1 squared, hasn't changed. And I'm plugging this in, so it's minus. Let me just show what this squared is. So E1 squared, the cross term, minus 2 E1 MC squared, and the MC term, plus MC squared. So this step is really why I went through the steps I did, because I saw that E1 will cancel out. Sorry, E1 squared will cancel out. So I end up with an expression. Let me distribute the minus. So plus and then minus. I have something that's linear in E1, and everything else is now constant. So I can solve this for E1. Well, let me write it down here. So solving it for E1, I get, so I'm moving this over. So M1 plus big M. So M1 squared plus big M squared divided by 2 big M C squared. Divided by 2 big M. And I actually haven't written down any factors of C because my plan is to just put in the correct factor of C at the end. I have energy here. On the right-hand side, I have masses here. M squared divided by mass, so it's mass. So what I really need is a factor of C squared. And if you actually did a careful algebra with the C's, you would see that you have C squared left over. Okay. Yeah, so that's the answer for energy of the muon. And at this point, I probably want to get a numerical value for it, and I can do the rest of the stuff with just numbers instead of algebra. So just so that it looks like it's correct, let's work out the numbers. So so let's see. Big M is 139.6, and small m, M1, is 105.7. 139, oops, 105.7. 105.7 squared plus 139.6 squared divided by 2 times 139.6. And I actually am not going to bother plugging in C because the way the units are specified, C is actually just cancel out. Right? I'm giving the rest energy, which would be mass times C squared. So I already pre-multiplied the C squared. So yeah, all right. So 109.816. That's the muon energy, 109.816. And from that, I can get muon momentum. Because the muon momentum in the correct units of mv over c, it would be, well, it would be the 139.6. So it's the rest energy of the pion, 139.6 minus the muon energy, this. And then I'm supposed to divide RC, that's done in the units. So 29.78. 29.78. The division by C is done in the units instead of in the numbers. Neutrino magnitude should be the same as this. That's what this equation says. So the magnitude should be 29.78. And neutrino energy, well, according to this, it's the momentum times C, And because of the c in the units, when you multiply by c, you're just changing the units from one to the other. You don't really change any of the numbers. So this is what the correct answer should be. Let's just double check. It feels about right. I guess I could do the show answer. Let me do submit. See if I. Yeah, so those are the correct answers. Now, part B is harder because what simplified part A was really being able to write this part in terms of one variable. For part B, you have to do it more generally. You have to, I think it's a good algebra practice. We have the time, unless someone else had more press. I think we can do this in like 20 minutes or so. So if this question okay, so this is harder than I remember, so we'll be sure to not put this exact version on the exam. But what I would do first is start out by laying out the algebra you're going to go through. Because when it comes to actually solving for the quantity, this is several steps, and I know what I'm doing, hopefully. And when you don't have as much experience as I do, you can spend a lot of time trying to get to this point here. And writing this out up to this point, this is already 3 out of 5 points on that part. And if you make any headway here, that's 4 out of 5. And really, the finishing it up correctly is a small portion of the problem. So spend more of your effort in correctly setting up your initial set of equations, making sure it's enough number of them, 3 equations, 3 unknowns, that sort of stuff. So part B. Since this approach worked well, let me rewrite part B using energy and momentum without involving gammas and V. And what I'm realizing is, nothing in the question is asking me for gammas and V. So I feel like I can save some effort by writing my energy and momentum conservation this way. So energy conservation, it would be mc squared is equal to E1 plus E2. And momentum conservation would be 0 is equal to P1 minus P2. And before, I had this one equation for one of those 2 particles. And what I have to write down as a reminder is now I have 2 of those, 1 for each particle. M1c squared is equal to E1 squared minus P1c squared. And M2c squared is equal to E2 squared minus P2c squared. All right. Kind of want to be able to do this all in a kind of, I want to be able to cancel out a lot of stuff all at once, but I don't know if there's a way to do that. Let me just think this through a little bit. Wonder, let me try using Lorentz Invariant. And this is what I mean by using Lorentz Invariant. I'm going to compute this without really knowing if this would be a good idea, just to see what I get. So this is my equation 1. This is my equation 2, right? And nothing stops me from writing down this. 1 squared minus 2 times c squared. Right? I can write down whatever I want. And if I do this for the left-hand side, and then do it for the right-hand side, equality still holds, right? So let me write that down. So I'm using my background knowledge of that this forms a Lorentz invariant. Energy squared minus momentum c squared, that's a Lorentz invariant. And I'm kind of hoping that will somehow simplify my calculation. It might not, we'll see. So when you write it out, the left-hand side is actually super simple because it's just this. It's just m squared c to the 4th power, that's left-hand side. And the right-hand side is at the beginning looking a little more complicated. This thing squared. So E1 squared plus E2 squared plus 2E1 E2. All right. And then minus this times C squared. So let me group this. Minus, I guess this thing squared times C squared. Actually, let me write it out this way. So P1C squared plus P2C squared. That's each of those terms that you get that you square them. And you have the cross term. So minus P1 minus 2 P1 P2 C squared. Good? It might initially look like I did I got a more complicated expression than I need, but I'm hoping you will recognize some terms that group up. This groups together to give me this. These group together to give me this. So, all right, let's write it out and see what I have. So I have, from this, I get M1C squared plus, here I have M2C squared. Then I have this, which I guess I need to write out. So it's a plus 2 times E1, E2 minus P1, P2. And then, sorry, there's a C squared there. C squared. All right, so I'm probably not done. Oh, I guess I can just use this equation. So this is where I do caution you. It's when you, so as a rule in algebra, once you have used the equations, you don't go back and reuse them, right? Because that's a way to get dependent set of equations. If you do it carefully, you can. You just have to be careful as you're doing it. So what I'm going to do is I'm going to go back, look at 2, use it again to eliminate P2 from here. So that I just have P1 squared instead of P2. So I have simply, so this will become, with that simple substitution, P1 squared. And I guess I don't see a reason not to do it with E1. E2. So solve this for E2 and then plug it in here. So, so solving this for E2, I should get E2 is equal to big MC squared minus E1. Plug it in here, and something didn't quite work out. This is supposed to be plus, right? What I wrote as minus here, it's actually plus. Good, so, okay. All right, now it'll work out. So when I plug this in here, this E1 times E2, what that'll be is this will be, so E1 times MC squared. That's fine. This is the part I wanted, minus E1 squared. Let me write out let me just write out just this expression here so that you can see the simplification I'm getting here, which may not be too obvious to people not used to dealing with the Lorentz invariant. So this thing in the parenthesis, what that is equal to is, I have this, that's fine, E1 MC squared. And it's the second part which is exciting for me. It's minus E1 squared. And since I'm going to put this inside this parenthesis, it goes back into being minus P1 C squared. Right? And this is what I recognize once again as M1 C squared squared. So my momentum is gone. My final expression here has only E1 as a linear term that I can solve for pretty easily. So, all right, so let me write out a version that simplifies all this. So this equation, I have m1c squared minus 2 m1c squared. So what I have really here is m2c squared minus m1c squared plus 2 E1 big MC squared. 2 E1 big MC squared. So left-hand side equal to this right-hand side. I can solve for E1 pretty easily. Solving for E1, I get E1 is equal to, combine all these mass terms on one side, it becomes big M squared plus small m1 squared minus small m2 squared. So this is what was before 0. Now it's not 0. That divided by this 2 big M. I think that's the, oh, sorry, I erased it, but that's the same thing we had before. 2 big M. And when you work out all the factors of c squared, you're going to get this whole thing times c squared again. So I guess I have the previous expression in my Wolfram alpha. So this expression here, that's what I had for my energy of the muon before, right? So this is the big M squared, small m1 squared. So the only modification I need to make is minus the neutrino mass squared. So neutrino mass, I'm assuming it's 0.19. So minus 0.19 squared. That's it. That's the only modification I need to make. So 109.816. 816, that, oh, all right. I'm not going to be able to, yeah, that's why the second part B asks for that more significant figures, because with the number of significant figures we had before, it doesn't work. You cannot distinguish them. So I have to write this out as 6538. Okay, that's the muon, and this is now 56755. And the neutrino, I think this is still good enough. Okay. 0.56755. All right, so it's saying to get it right to the 4th place to the right of the decimal. So for the muon energy, I will say 109.7775. All right. Now with the settings I changed, does it let me resubmit again, or I have to?
No, you can just submit.
Yeah, okay. Oh, so okay, so it behaves that way for you guys as well. Good. All right, so let me just do submit. And that one is correct. Now to get the rest, so you'll be working back through the same expressions again. So now that you have the muon energy, you can just solve for the muon momentum numerically here. And I would just recommend going through the calculator. So yeah, so that's how you work through it. And this is sort of, this algebra that I did is a bit of a surprising place where Lorentz invariant is useful. That because you're dealing with a simple reference frame, you might have kind of, using this gamma and v might have been your first instinct. And when you actually do the calculation, the simpler way to do it is through the energy and momentum relationships, and at some point using Lorentz invariant. I will tell you this, in most of the special relativity dynamics problems, computing Lorentz invariant, unless you know the obvious way to do something algebraically, doing this is one way of getting a simpler expression. With one exception. When you derive the Compton scattering formula, Lorentz invariant doesn't help. So there's really only one way to derive the Compton scattering formula. That's the way it's done in your textbook. And for your exam, you will never have to derive it. I wouldn't ask that on an exam. But if you ever have to derive a Compton scattering formula, look at how your book does. That's the only way to do it. It doesn't use the Lorentz invariant, and it's kind of one exception where you just have to go through it the right way.